In this next section, we're going to talk about the challenges of dealing with real-world data and some of the quirks you might run into. So let's start by talking about the bias-variance trade-off, which is kind of a more principled way of talking about the different ways you might overfit and underfit data and how it all interrelates with each other. Let's take a look. So one of the basic challenges that we face when dealing with real-world data is overfitting versus underfitting your regressions to that data or your models or your predictions. And when we talk about underfitting and overfitting, we can often talk about that in the context of bias and variance and the bias-variance trade-off. So let's talk about what that means. So conceptually, bias and variance are pretty simple. Bias is just how far off you are from the correct values. So how good are your predictions overall in predicting the right overall value? If you take the mean of all your predictions, are they more or less at the right spot? Or are your errors all consistently skewed in one direction or another? If so, then your predictions are biased in a certain direction. Variance is just a measure of how spread out, how scattered your predictions are. So if your predictions are all over the place, then that's high variance. But if they're very tightly focused on what the correct values are, or even an incorrect value in the case of high bias, then your variance is small. So let's look at these examples here. Let's imagine that this dartboard represents a bunch of predictions we're making where the real value we're trying to predict is in the center of the bullseye. So starting in the upper left-hand corner, you can see that our points are all scattered about the center. So overall, the mean error comes out to be, pretty close to reality. Our bias is actually very low because our predictions are all around the same correct point. However, we have very high variance because these points are scattered about all over the place. So this is an example of low bias and high variance. If we move on to this one, to the upper right corner, we see here that our points are all consistently skewed from where they should be, to the northwest here. So this is an example of high bias in our predictions, where they're consistently off by a certain amount. And we have low variance because they're all clustered tightly around this wrong spot, but at least they're close together, so we're being consistent in our predictions, and that's low variance. But the bias is high. So again, this is high bias, low variance. This example in the lower left corner, you can see that our predictions are scattered around the wrong mean point. So we have high bias, everything's skewed to someplace where it shouldn't be, but our variance is also high. So this is kind of the worst of both worlds here. We have high bias and high variance in this example. And finally, in a wonderful, perfect world, you would have an example like the lower right image here, where we have low bias, where everything's centered around where it should be, and low variance, where things are all clustered pretty tightly around where they should be. So in a perfect world, that's what you end up with. But in reality, you often need to choose between one and the other. So let's take a look at this example. A little bit of a different way of thinking of bias and variance here. So here we have a straight line, and you can think of that as having very low variance relative to these observations. Okay? So there's not a lot of variance in this line, low variance, but the bias, the error from each individual point is actually high. Okay? Now contrast that to this overfitted data here, where we've kind of gone out of our way to fit these observations. This line has high variance, but low bias because each individual point is pretty close to where it should be. So this is an example of where we traded off variance for bias. Now, at the end of the day, you're not out to just reduce bias or just reduce variance. You want to reduce error, right? That's what really matters. And it turns out you can express error as a function of bias and variance. So error is equal to bias squared plus variance. So these things both contribute to the overall error, with bias actually contributing more. But keep in mind, it's error you really want to minimize, not the bias or the variance specifically. And an overly complex model will probably end up having a high variance and low bias, whereas a too simple model will have low variance and high bias. But they could both end up having similar error terms at the end of the day. So you just have to find the right happy medium of these two things when you're trying to fit your data. And we'll talk about some more principled ways of actually avoiding overfitting in our forthcoming lectures. But it's just the concept of bias and variance that I want to get across, because people do talk about it. You're going to be expected to know what it means. If we tie that back to some earlier concepts in this course, for example, in k nearest neighbors, if we increase the value of k, we start to spread out our neighborhood that we're averaging across to a larger area. So that has the effect of decreasing variance because we're kind of smoothing things out over a larger space, but it might increase our bias because we'll be picking up a larger population that may be less and less relevant to the point we started from. So by smoothing out k and n over a larger number of neighbors, we can decrease the variance because we're smoothing things out over more values, but we might be introducing bias because we're introducing more and more points that are less and less related to the point we started with. Decision tree is another example. So we know that a single decision tree is prone to overfitting, so that might imply that it has a high variance. But random forests seek to trade off some of that variance for bias reduction. And it does that by having multiple trees that are randomly variant and averages all of their solutions together. So kind of like when we average things out by increasing k and n, we can average out the results of a decision tree by using more than one decision tree using random forests. Similar idea. So that's the basic idea of bias variance and the bias variance trade-off. I hope it makes a little bit of sense. Let's move on. So that's bias variance trade-off. Again, there's sometimes a decision you have to make between how overall accurate your values are and how spread out or how tightly clustered they are. So that's the bias variance trade-off, and they both contribute to the overall error, which is the thing you really care about minimizing. So keep those terms in mind.